Gear ratios. Gear ratios are very similar in concept to mechanical advantage. Let's first go over some of the variables that are going to be in this. N is the number of teeth in the gear. D is the diameter of the gear. The Greek letter tau, which looks like this, is the torque of the gear. The Greek letter omega is the angular velocity of the gear, and that means something, for example, like revolutions per minute, revolutions per second. It's a lowercase Greek letter omega. So using those variables, here's what the gear ratio is defined as. GR for gear ratio. It's equal to the number of teeth going out divided by the number of teeth going in. Now let's quickly discuss what the in and the out means. In is the gear that is the driver. Out is the gear that is being driven. Relating that to mechanical advantage, the driver is known as the effort. The driven is the resistance. So number of teeth going out divided by number of teeth in, which in turn is equal to the diameter of the out divided by the diameter of the in, which in turn is equal to the torque, tau, on the out divided by the torque coming in, which in turn is equal to, now this last one's a little bit different. This last one is the angular velocity. This one is the opposite of the rest of these. Angular velocity of in over angular velocity of out. So memorizing this is important. Some previous students have said naut over nin equals dout over din equals tout over tin. And then you just have to remember angular velocity is the opposite of those. Naut over nin equals dout over din equals tout over tin. That's gear ratio, which equals win over wout. I'm just going to highlight this last one because it is, once again, a little bit different. Let me show you how to apply that. I'm going to have a picture here of a couple gears. I'm not going to draw the teeth because it takes time. I'm just going to draw a couple circles. Here's a gear. Let's say that that gear is 6 inches in diameter. Here's a gear beside it, and let's say that that gear is 2 inches in diameter. Let's also say that the gear on the right is in, meaning it's the driver, and the gear on the left is out, meaning it's what's being driven. This would be the effort, this would be the resistance. Some other things that you'll be told here. Perhaps you'll be told the revolutions per minute and the direction that this is moving in. Let's say that the driver is going counterclockwise at 60 revolutions per minute. 60 RPM. Which would force the driven one to go in the opposite direction. And let's say that it is at 20 RPM. Let's also assume that the driver has 6 teeth, N is for teeth, and the one that is being driven has 18 teeth. And finally, let's assume that you're also told the torque of each of these. Let's say that the driver has a torque of 40 foot-pounds, and the driven has 120 foot-pounds. So already as I've labeled this, I don't like how I've labeled it. If you're going to have in and outs, and you're going to have two different n's, you can't just say n is 18 and n is 6. You have to make sure you say n for the in, n for the out. Tau for the in, tau for the out. That's important. So using what we know about gear ratios, we could say the following. Gear ratio equals nout over nin, which equals dout over din. Please understand that these little words that I'm writing here, they're supposed to be subscript. I'm writing them a little bit big, but they're supposed to be subscript, which in turn equals tau over tin, which equals angular velocities backwards. Angular velocity of the in over the angular velocity of the out. Let's see if this works for this problem with these numbers. Number of teeth coming out, 18. Number of teeth going in, 6. That should be equal to the diameter of the out, 6 inches, over the diameter that's coming in, 2 inches. And I made a mistake when I wrote my 18 and 6. You have to use labels. If you don't use labels, it's wrong. 18 teeth, 6 teeth. That should equal the torque of the out. The torque is 120 foot-pounds over the torque of the in, which is 40 foot-pounds. That should equal the angular velocity of the in, 60 RPM, over the angular velocity of the out, which is 20 RPM. Now, are these all in fact equal? Well, your labels cancel each time, because if you divide something by itself, it cancels. 18 divided by 6, that's 3. 6 divided by 2 is 3. 120 divided by 40 is 3. 60 divided by 20 is 3. We can conclude from this that the gear ratio is 3 to 1. It will always be, assuming that there's no friction, and there's always friction, but we're just doing theoretical calculations, that these four things will be identical. In this case, the gear ratio is 3 to 1. Here's another example. Here's a gear train. Once again, I didn't draw the teeth, but I wrote down how many teeth each of these have. We got gears A, B, C, and D. Now the picture doesn't say which one's the driver and which one is being driven, so we really shouldn't assume unless we're forced to. But if you look at the question, it says find, the first question, the purple, find the gear ratio of A to B. Since A is first in the sentence, we're going to assume that A is the driver and that B is being driven. So this is the effort and this is the resistance. That's our assumption. So how do you find gear ratio? Well, gear ratio is the number of teeth going out divided by the number of teeth coming in. Number of teeth on the resistance, gear B, is 20. Number of teeth coming in, the effort, is 30. So that is 2 to 3 is the gear ratio, or 0.6 repeating, if you will. Gear ratio for the second question of B to C. So B is in, C is out. B is first, we assume it's in. The number of teeth on the out divided by the number of teeth in. That would be 40 teeth divided by 20 teeth, which is 2 to 1, or 2. Third question, gear ratio from C to D. C would be in, D would be out. So from C to D, that would be number of teeth out, number of teeth in. Out is 15. 40 is for the in. divide both those by 5 and get 3/8. So that's the gear ratio from C to D. So I just took away the work and wrote down the answers there. Gear ratio from A to B is 2/3, from B to C is 2, and from C to D is 3/8. So the next question is, what's the total gear ratio of this train? Well, this makes this a compound machine because there's more than one. It's not a compound gear, but we could say it's a compound machine in that there's more than 2 gears. So anytime you have a compound machine and you want to find the total mechanical advantage or total gear ratio, you just multiply each of those together. So that means that the gear ratio of this entire thing, let's just say of total, it's going to be the product of each of these. It's 2/3 times 2 times 3/8. Doing some cross-canceling. 3 divided by 3 is 1. We can take then 2 times 2 and get 4. 4 divided by 8 is 1/2. Here's something really important. There's an important note here. The gear ratio of this entire train here is 1/2. If it's just a gear train, not a compound gear train, you can find the same answer by just taking the gear ratio of the first gear to the last one. Like in this case, once again, it's always nout over nin. Number of teeth for a gear D is 15. Number of teeth on gear A is 30. It is not a coincidence that that reduces to 1/2. So this is supposed to illustrate the point that the gear ratio can be found. You can do it from each gear in succession, or you can just do from the first to the last. But this only applies to just a simple gear train. It does not apply to a compound. Compound meaning 2 gears on the same axle.